Annex A suggested approach to measure and evaluate correctly push and pulling forces in different working scenarios. Introduction and goals of the new annex. In this Annex A, we want to propose practical but at the same time precise solutions which allow a proper assessment of the forces obtained for pulling and pushing tasks. Evaluation was precision is important because with them the values of the risk indexes are calculated. This proposes to mainly use digital dynamometers, see Annex D. Therefore, procedures are presented for a more easily applicable estimation of the consistent curve, techniques for more objective identification of the starting point of the initial and maintenance phase of the consistent curves, innovative techniques of analysis of push and pull tasks carried out on rough pavement, garbage collection, paths with curve, push and pulling action of objects without wheels are also proposed. In practical, our objective is to improve the actual Annex B, where the basic suggestions for measuring push-pull force are proposed but in a shortly way. In this part, in fact, we can see the procedure described for taking correct measure of force. The suggestions are sufficiently correct. And in this part, the actual Annex B speak about the necessity to measure the initial force and the sustained force in the different two phases of the push and pulling curve, and to repeat different measures of the same path until you have made at least 3 consistent measures. Consistent measures should not differ in each other by more than 15%. And for the peak of force, you have to measure the highest force between the 3 consistent curves. And in the same way, one have to measure the average measure of the consistent curve in the sustained part of the curve. So we conserve this criteria, but we try to propose more operative way to obtain this important data. Pushing and pulling forces evaluation, main definition. The current figure shows the force applied when pushing and pulling a card in an ideal push and pulling task. In this case, the initial and sustained force can be easily identified. Initial force, sustained force. Example 1, figure B, shows 4 sets of force measurements repeated along the same path, as suggested in ISO 11228.2 for determined consistent curves, in a push task carried out on smooth asphalt. In this case, the measured forces are characterized by limited fluctuation. Example 2 in figure C shows force measurement along a path over an uneven surface with significant fluctuations. In this case, evaluating consistent curves and pinpoint the initial and sustained forces may be more complex. To achieve an easier and practical assessment of consistent curve, we suggest 4 operating steps. First, a qualitative consistency evaluation of force curves repeated for the same path. Identification, the start of the sustained phase. Quantitative consistency assessment, consistency evaluation when the curve do not present evident initial or maintenance phases. And now we explain all the different steps to obtain correctly the consistent curves. First step, qualitative consistent evaluation of force curves repeated for the same path. A preliminary evaluation of the consistency can be done simply by analyzing the graphs of the different curves of force measurement of a given path, data obtained with digital dynamometers. As a preliminary step, before tackling the search for quantitative consistencies aimed to respecting the 15% of the differences between measurements of the same path, we recommended the qualitative evaluation of the consistency itself, following the procedure expressed in the following slides. More difficult to explain than to observe, it is simply a matter of visually comparing the curves relating to the force measurement and eliminating the anomalous curves. We have created a spreadsheet in Excel for representing the curve force obtained with digital dynamometers, allowing to clean them qualitative and quantitative both, and to proceed then in the final risk assessment. It can be downloaded free of charge from this site. First step, eliminate any series of curves which obvious artifact or execution errors. Criteria, common sense. Look at the picture of the curve. In these examples, we have two series of curves with error or artifact, the blue curve and the yellow good. Eliminate them, we now can see two series with qualitative consistency. Second step, try to align the initial force peak. It is preferable to discard the non-aligned force curve if the operator cannot use an alignment solution. We can see two examples with curve not aligned. First example, other example. Locate the start of the force curves at the point where the curve for the initial phase begins to rise. So the curve begins here. We have to cancel this part. Also in this second example, we have to cancel this part. And any forces lower than 0.5 kilogram force were eliminated from the dataset, thus avoiding the risk of included technical anomalies or noise. The qualitative consistencies is more difficult to explain than to observe. It is simply a matter of visually comparing the curve relating to the force measurement and eliminating the anomalous curve. Look at this example. In this first example, you can see that the blue curve is completely anomalous. In this second example, the yellow is completely anomalous. Again, in this example too, the yellow curve is completely anomalous. In this case, we can observe a cause. Probably all the evaluation is not consistent, so we have to repeat the evaluation. Also in this case, the four curves are completely anomalous. In this case, the curves are not aligned. The free software that we prepare in Excel help the user to qualitative cleaning the curve from the anomalous evaluation. After the qualitative cleaning of the curve, we have to proceed with identification of the start of the sustained phase. For the correct calculation of the forces both in the initial and sustained phases, it is first necessary to define the criteria that establish the start times of those phases. The procedure is easy for the initial phase, which begins at the point where the curve begins to rise to overcome inertia. Couplings for the imagined phases, given that measurement of the curve series of the same path overlap, especially where there are numerous fluctuations due to uneven pavement. Look this example. In the first example could be easy. In the second example is very difficult. By graphical depicting the average curve, here indicated in red picture, after qualitative cleaning for the path travel, it is easier to determine the start of the sustained phases. In the case of push and pulling along a smooth path, the start of the sustained phase can be identified as the time corresponding to the lower point force value immediately following the higher point. Down, high. More complex is the identification of the start of the sustained phases for push and pulling over rough terrain, here again represented with an average curve in the red figure. Also using this average curve produced to make easier the determination of the beginning of the sustained phases, it is difficult to find this point. A common sense decision is to be made. If it is difficult to find this point, proceed as indicated in the next slides dedicated to methods for evaluating forces where the initial and sustained phases are no distinguishable. Now we can proceed with the quantitative consistency assessment as suggested in the actual ISO. It now remains to determine whether the force curves are also quantitatively consistent, that is, if they differ from the average by no more than 15%. Taking the initial phase and the sustained phases separately, the percentage differences of each series are calculated versus the corresponding total average. The average values of force measured on all the qualitative cleaned series was taken as a reference parameter for reading the percentage deviation calculated for each series for the entire duration, the initial phases, the marginal phases. The average forces is to be calculated now for each single series, again separately for total series, average of the initial phases, average of the maintenance phases. For each of them, the percentage differences was calculated with respect to the total average calculation on the 4 series together. The tables here present better, in an easier way, the results of the calculation of differences and the consistencies between the 4 curves in example 1. Example characterized by the 4 series of curves with no main fluctuations, with good terrain. Calculation of the consistencies for the initial phase. Here we can see the force values in kilogram calculated as the average of the peaks of the 4 series only in the initial phases. Now we have to calculate the peak of force presence in each of the 4 series of curves present in this evaluation. Having the peak of force on each series, we can calculate the percentage difference of each of them, considering the references with the average of the peak of the 4 series in this part. We have to consider the maintenance phase. Again, we have to calculate the average force values calculated considering all the 4 series of curve. And after we have to calculate the average force specific for each curve present. Now it is possible to calculate the differences between the average values of each force between with the average force values for all the series. We can see all the differences for the initial and maintenance phases as less than 15. So in this case, all the 4 curves considered, both for the initial and maintenance pair, are consistency. In this second example, unlike the example viewed previously, the push of the trolley on rough ground generates large oscillation of force along the entire path. Large deviations can be seen between the 4 superimposed graphite paths, with difficulty in defining the starting point on the maintenance phase. The coarse curves called Series 1 and Series 2 differ greatly from the average of the 4 curves, well over the 15% suggested, unlike Series 3 and Series 4, which remained under 15. Series 1 and Series 2 therefore be eliminated because they are not consistent. However, on the basis of a further qualitative evaluation, observation of the graph, the wheezily inconsistent series turn out to be only the Series 2. In fact, by cancelling it for the graphic A, the graphic consistency of the 3 remaining curves still appear at least qualitatively evident. Graph B. In summary, the practical suggestion for choice of the consistent path measurement is certainly that of the evaluating the deviation of 15% for the average, but also observing anyway the graphic obtained before only with the qualitative consistency, especially in presence of measurement performed on uneven ground, which produces a strong oscillation. Indeed, in these cases, eliminating all the entries with deviation from the average of more than 50% will risk introducing underestimation on the final risk. For the determination of sustained force, average of the applicable values in the case of consistent registration, the following methodologies is proposed, determining both the average values as suggested in the actual ISO, but also the values corresponding to the 75th percentile. The reference to the 75th percentile can be useful to bring out the presence of the highest level of force, so important in generating any biomechanical overload pathologies without flattering them excessively as the average values does. In this chapter, we suggest how to do when the consensus evaluation of the curve have a problem because the initial and marginal phases are not so evident. And we propose 3 steps. Evaluation of force curve measured over an even ramp surface, evaluation of curves measured along paths with turns, and evaluation of force curve measured pulling and pushing object without wheels. We start with the new proposal for evaluating force curve measured over uneven and rough surface. The figures show example of measurements for pushing-pulling of relatively full four-wheel cars over different types of rough terrain, sand, fine gravel, cobblestone, dirt roads, etc. All the measurements depicted graphically were obtained with a digital dynamometer. The first observation that can be made is that there is no initial phase followed by the typical sustained phase. It should be noted that in all of these situations, the consistency of the successive measurement based on the principle of deviating less than 15 from the mean is not really applicable. The actual ISO standard does not specifically address how to deal with the assessment of these conditions. Therefore, the following alternative solution can be adopted. Consider the path measurement as a single path without breaking down it into initial and sustained phase. Record only the curve with qualitative consistencies, since quantitative consistencies cannot be assessed. Look for the highest peak over the entire path of travel to be taken as the maximum force exerted instead of the initial force. Calculate both the average value and 75th percentile again over the entire path. And now how to proceed for the evaluation of force curves measured along path with turns. Loads may need to be pushed and pulled along paths with turns. Figure A shows forces measured along a path with multiple turns. It can be seen that just before entering into a turn, the cars slow down and there is a significant reduction in the amount of force exerted, followed by a recovery and a new peak, which can be considered representative of a new initial phases that start when the turn is completely. Look here, turn, start again, turn, start again, turn, start again, etc. In situations such as these, which are very frequent in hospital, the problem arises when it comes to choosing criteria for calculating the representative initial and sustained force along a path with different types of turn followed by straight sections. In figure B, 3 turns are shown, extrapolated from the total path of travel. On this, that could be considered as a stand-alone path. It is often difficult to locate the initial peak force and the beginning on the sustained force. Look here, this is only a peak, and this the peak is in the center of the curve. When paths of travel include frequent successive turns, the recommendation is to assess the forces following the same rules as for paths over uneven surface that we spoke before, to calculate the maximum peak and sustained force over the entire path is the only solution possible. Last situation, evaluation of force curve measuring pulling pushing of objects without wheels. The attached figure shows a series of consistent curves obtained by pushing objects, sort of drovers resting on the ground without wheels, part of machinery under maintenance. The graph illustrates how in this case the distribution of forces shows an evident peak phases, but without the maintenance or sustained phases. For the estimation of exposure risk, we recommended using the method already proposed for the analysis of force curves measured from rough terrain. The most specific suggestion is consider the path reading as a single path without breaking down it into initial sustained phases. Record only the curves with qualitative consistency and quantitative consistencies. Look for highest peak over the entire path of travel to be taken as the maximum force exerted instead of the initial phase. Calculate the average values and the average and 75th percentile again over the entire path.